So in this video, we're going to be talking about a general purpose strategy for choosing parameter values without looking at test. And it's one of my absolute favorites from data science. So I just think it's so clever. I think it's just a really smart way to get around a tough problem, and it's called cross-validation. So to remind you of the problem, if we're trying to pick the number of variables in our model or the number of splits in our tree or which variables go into our model or the best value of k and knn, any one of these parameters that our models rely on, it is not legal to make that decision considering test in any way. And that is a huge bummer. What we would like to do is find the value of k and knn, for instance, that minimizes the error on test. What we want to do is find the right combination of variables that minimizes error on test, and so on and so on and so on. But that's not okay. That's not okay. The whole point of test is to be an objective test of model quality. If we allow test to start influencing our model's form in any way at all, that test data has become training data. Remember, training builds the models and test only evaluates the models. So in an ideal world, if you have an infinite data lake, as much data as you possibly could conceive of, you use each test exactly once. It is a burner. Like, you use it and then you throw it away and you never look at it again. And you look at the new test and you throw it away, like over and over and over again. In most data applications, you can't do that, but that's the intellectual, honest way to think about this particular issue. And so we need to get around this. We need to get around this idea, and the best way to do this is k-fold cross-validation. So let's talk about what that big term means. Here's the idea. We're going to take our training data set and we're going to split it into pieces. Here, k equals 4. So this is 4-fold cross-validation. And this is only training. Test is nowhere to be found. I've locked test in a box in another state. We can't even see the thing. This is only training, okay? We break it into pieces. Here's the idea. We consider pieces 2, 3, and 4 as our training, and then we're going to call 1 like a mini test, okay? The reason we call this cross-validation is that this is often called the validation partition, just to keep it separated mentally from test, and people call it validation. I mentally think of it just like a little mini test, but call it what you want. It's the same idea. So we build the model on pieces 2, 3, and 4 using that as training, and then evaluate that model on piece number 1. Notice that this is totally legal. This is totally legal because the real test, the true test, is locked away safely. We're only dealing with training. We do this over and over again. We build on 1, 3, 4, we apply to 2. We build on 4, 1, 2, we apply to 3. And we build on 1, 2, 3, and we apply to 4. Now, why are we doing this? Why are we spinning this validation partition around across all of the different segments here? What's the deal? Well, here's the idea. Each one of these pieces is going to be noisy. Like, it's going to be kind of a weird representative. And what we want to do is kind of smooth out that noise. So I build the tree with piece number 1 as my mini test, as my validation. I build the whole tree with piece number 2 as my mini validation, with piece 3 as my mini validation, and piece 4 as my validation. Okay, and remember, the other 3 pieces are acting as training in all these cases. What I do then is I look at the performance if I limited all of these trees to size 2. I'm sorry, size 2 after 1 split. 2 leaf nodes is 1 split. So after 1 split, and I see what the average performance is, what the average error is, then I say, okay, across all these trees, if I limited them to just 2 splits, what would the average error be? Average across all of these. Notice some of them might do really well, some of them might do poorly, just by chance. And I want to average out those kind of random fluctuations and get an idea of underneath, like, what can I expect to see? I keep doing this, 3 splits, 4 splits, 5 splits. It's all good. And then I can plot this thing. So what do I want to do? How do I actually find the best size? You build these k different trees. You keep track of the performance when you average across the same size or same number of splits across all the trees, and then we see what it looks like. So here's something we would see. So again, this is our most important figure in the course. Now with an addition, this is what I would see, something like this, if I were to plot the cross-validation error on the same plot. So what I hope to get is some kind of estimate of what would happen on test. And that's because I really am kind of like using 1, 2, 3, and 4, those different pieces as little mini tests. It's not going to be perfect. It's not going to perfectly match things, and that's why I made it all squiggly. It's kind of like an estimate, okay? But it's better than the other choice, which is just to be like intellectually dishonest and ultimately self-destructive by using test as part of training. If we do that, we're going to fool ourselves into thinking that our model is better than it actually is. And this is ultimately a huge issue. So by cross-validating, we can kind of get an idea of what the model would do on test without actually using test at all. Amazing, right? Now here's the good part, because I can normally if you're teaching this in class, when students finally start to understand what this concept is, you see their eyes get like really big and like they're super worried because they're like, oh my God, are we gonna have to do this by hand? No, most software packages are included, and even individual methods within R do this automatically. You don't have to do these things by hand. So for instance, when we do pruning, it's going to automatically do tenfold cross-validation for you. You don't have to do anything. Like this is one of the things we've written, either like the people that wrote the methods wrote for you, or Babson faculty have written for you, because it's not worth, the concept is extremely important. The implementation is not so important. It's the type of thing that if you do this for a living, eventually you do yourself. And I've done like, it's funny because like the very first, if I'm doing a new data science project and I have a pretty limited data set, the very first thing I do is develop a cross-validation partition system, because it's so important. I know it's going to come in, if it's not important immediately, it will be important very soon. And so the very first thing I always do is get my cross-validation set up in place, and then I can start playing with stuff. But it's just, I know it's going to be important, so I might as well just get done at the beginning. So anyway, this is the big idea. It's useful in trees, it's useful in KNN, it's useful in linear and logistic regression. It's useful all over the place. And so it's just a good general purpose idea to keep in your mind when you're trying to decide how to pick these important values in various data analytics strategies.